without further ado, let's start with Daniel from Ben-Gurion University, Masters at Ben-Gurion. We'll talk about multimodal in MRI.
Thanks very much. Okay. Hi, I'm Daniel. This work is a part of my master's thesis in electrical and computer engineering at Ben-Gurion University, together with the supervisor Tammy, and collaboration with McGill University, Tal Arbel, and Brennan. So a patient coming to the doctor's office says, "Doctor, I think I'm pregnant." After several tests, the doctor says, "Well, the urine and blood tests were negative, so there's nothing there, and the ultrasound also, I didn't see anything unusual. Your age is, you're quite old, so Yossi, you're not pregnant." Clinicians are expert in integrating data of different sources, such as clinical measures, imaging, patient sensations, overall observations before making decisions. This task is still challenging for intelligent machines. Indeed, visual language models are outstanding in text-image fusion tasks. However, in most cases, text describes the image in some manner. This is not always the case while fusing imaging and tabular data in medical domain. In this domain, information is often complementary and has no clear semantic correspondence. For example, opacity in chest X-ray may indicate infection, but a blood test is needed to determine whether it's a viral or bacterial. Of course, our focus is on integrating imaging and tabular data, usually derived from patients' electronic health record. Imaging data and tabular data are completely different types. Moreover, tabular data are usually mixed types, like categorical, ordinal, continuous, discrete, how this can be meaningfully integrated. A naive approach involves projection into feature spaces followed by concatenation. However, this is a high-level feature descriptor fusion, neglecting the image, the spatial context in the image that is preserved in the convolutional layers. In a recent approach, the limitations is partially fixed by applying affine transformations to image features inside the CNN, where the transformation parameters are generated from tabular data. Intuitively, it uses the tabular attributes to highlight specific image features. Still, using a linear transformation, such as affine, is restrictive. In this work, we present a conceptually different approach. Our key idea is to use the tabular data as a prior to the image analysis task, and for this purpose, we use hypernetworks. While hypernetworks are not uncommon, they are used in the fusion of multimodal for the first time here. So what are hypernetworks? Well, the key idea, the general concept is meta-learning. A network generates parameters for another network called the primary network, which is designed for a certain task. In our case, image analysis. The hypernetworks takes as an input the tabular data and generates some parameters for the primary network. Those generated parameters are called external, and the rest of the parameters are called internal. The internal parameters of both networks are learned in an end-to-end manner. This way, during backpropagation, the gradient flows from the primary network to the hypernetwork, directly updating the internal parameters of both networks, thereby indirectly affecting the external parameters. The primary network can be any type of network. Specifically, here we choose a CNN. The main task of the hypernetwork is to embed the tabular data. It can be done in many forms. We choose to use a simple MLP in this case. This embedding is followed by linear layers that generate weights and biases for the designated layer. The designated layer can be of any type of operations. Here we use them both convolutional and linear layers. In order to learn a layer-specific embedding, we use K hypernetworks with 4K designated layers. Assuming that low-level image features are usually independent of the tabular data, we choose the designated layers to be high-level feature layers. It is both intuitive and empirically works better. The loss has two parts: task-specific loss and the weight decay regularization term. I would like to mention some challenges and important topics. However, I will not get into too much details here. Recall that the loss backpropagates from the primary networks to the hyper network. Therefore, it should optimize both the image analysis and the embedding space. We would like to map the tabular data to a feature space with a meaningful structure and learn attribute interactions. In addition, we have two sets of parameters: the internal and the external, that are generated by the hypernetworks. Their initialization is important for convergence. However, the external parameters cannot be directly initialized through the initialization of the hypernetwork's internal parameters. So we have to initialize the hypernetwork internal parameters to affect them. Another challenge stems from the fact that the tabular data is of clinical studies, and it involves healthy volunteers. So why should they receive invasive treatment? Therefore, their group have missing values in their data, and this may introduce biases. We validated our method on two brain imaging related problems. The first is brain age prediction. We want to predict the brain age based on an MRI, and we add the subject sex, a tabular data with one attribute. And the second one is Alzheimer's classification. We would like to distinguish between three classes: healthy, sick with Alzheimer, and mild cognitive impairment, which is challenging to classify intermediate stage between those two. Looking at brain MRI acquired from individuals at different ages, we considered a very clear aging trajectory. Now, for the million-dollar questions: do female brains look younger? The data we used for this experiment is composed from 19 different data sets with around 27,000 healthy brain scans. This comparison highlights the differences between using imaging only and fusion with our methodology in purple. As shown, we achieve lower error rate, indicating that our methodology can be effective for the fusion task. Next, we tested the Alzheimer's classification, training the network to discriminate between those three groups. We used the EDNI dataset, and you can see here the tabular attributes. We compared our method in purple to other approaches. There is imaging only, tabular only predictions, the naive concatenation, and more sophisticated affine transformation we discussed earlier. The main takeaway from this one, of course, is that our method outperforms all of the rest in all of the other metrics with statistical significance. To conclude, hypernetworks have been used before, but this is the first time they're been used to multimodal fusion, specifically for image and tabular data integration. Again, the main idea is to use the tabular as a prior for the image analysis. I would like also to indicate that the application of this method to other architecture and other data modalities is pretty straightforward. Thank you all.